Right, so obviously we know what slope is, right? We know slope is rise over run. Represented by m, we all know that. If we want to think of it in terms of a formula, which I would discourage you from doing, really don't. Just think of it, always think of it in terms of a picture. If you remember formulas, you'll just forget them, but if you think about things in terms of pictures and concepts, you won't ever forget them. So if we call these random points x1 and y1, technically x sub 1 and y sub 1, and x sub 2 and y sub 2, we just call it x1 and y1. What do those really mean? Because this is sort of a subtle point that we're going to use again and again all year. How are these different than just saying x and y? Well, they are a little bit different, yeah, and it's a really subtle thing. What do you think? Yes, sir?
That way both the points are at the same point.
So, okay, so it distinguishes one point from the other point, and they're meant to represent specific values. Even though we don't write them as specific values, we call them parameters. They're not really variables. I mean, they're meant to be actual point values, ordered pairs that correspond to a point. We don't pin ourselves down to saying it's always going to be 1, comma 2. I mean, it could be anything, but they're meant to represent individual points on a line, right? And so if we've got these 2 points represented by, point 1 and point 2, then we just know that slope is rise over run, right? So change in y would be our rise. We all know that, right? Change in y over change in x. And sometimes we write that as, there's a different way we can write that. And let me see. We do this a lot, like when we get to calculus, this will be how we'll write stuff. We'll write that as delta y over delta x. Okay, what does delta mean? Do we know? Yeah, change. It means changing. So anytime you see a delta in math, it's the change in something. Okay. So change in y over change in x. Okay, questions? Make sense? I mean, I'm going to just zip through this. So if we've got, there's point 1, there's point 2, we're just going to find the change in y over the change in x. You don't have to follow a specific formula. You can do this in your head. You can just say the difference in the y values over the difference in the x values. But what's wrong with what I'm going to do here? What if I calculate the slope to be 5 minus 1? So 5 minus 1 over 2 minus negative 3. What did I do wrong there? Okay, yeah, I switched the order of the points around, didn't I? Right, and that's going to change the sign of the slope. So it doesn't really matter which one you start with. It doesn't have to be officially like the second one minus the first one. Do whatever's convenient, but you just have to be the same both times, right? I would have to flip those around. Okay, and that's a pretty common mistake. It really is. I see that a lot in algebra too. All right. So get an answer of negative 4/5. Does that, one thing you should always do also in math is just see if it makes sense. Does that pass the ridiculousness test? Right? I mean, does that seem reasonable? Negative 4/5 is pretty close to negative 1, right? A slope of 1 is a 45-degree angle. That seems reasonable. Is the fact that it's negative, does that make sense? How come? Oh, it's decreasing. Okay, it slopes downhill from left to right. Good. Okay. Good. So we can classify lines by slope. Once again, just a little quick review here. A line with a positive slope is a rising slope. Negative slope is a falling slope. What about a zero slope? What's that? Okay, that's going to be horizontal, isn't it? Zero slope is horizontal line. Yeah, vertical is going to be undefined. Good. Okay. All right. Okay, and real quick as an example, like if we tried to do this guy right here, we're gonna find the slope between these points. I could do something like 5 minus -1 is gonna give me 6 on the top, 2 minus 2, 0, so I'm getting 0 on the bottom, so obviously, that was a tough one. So anytime I get 0 on the bottom, I just want to connect some dots for you here. That doesn't work, does it? Right? That's undefined. That's one of the two things we've always said for real numbers you can't do. You can't take an even root of a negative number and you can't divide by 0. That's why it's undefined. What about this also? If you think about this graphically, what about these 2 points makes it pretty obvious that they're vertically aligned?
Both on the x level.
Yeah, the fact that the x values are identical means they have to line up vertically, right? So it's all, I mean, it all kind of comes together in Algebra 2 a little bit. Okay, so here's another one. What about which of these, I'm going to pick 2 lines here. And I want you to tell me which line is steeper. A line with a slope of -3 or +1. -3, yeah. Does it really matter what the sign is if we're talking about steepness? No. No, the sign's just telling us if it's rising or falling. It's the absolute value of the slope that's telling us how steep it is, right? Okay, what's true of lines that are parallel? What can you say for sure about their slopes? Have to be the same, right? Good. Yeah, that's a pretty easy one. What if they're perpendicular?
90-degree angles.
Okay, they're at 90-degree angles. That's what it means to be perpendicular, right? But what's that say about their slopes? Okay, opposite reciprocals. Good. So the slopes are equal, they're parallel. If they're opposite reciprocals, right, then they're perpendicular. Another way to think about that is that the product of the 2 slopes is -1. I always think about it as opposite reciprocals. That seems a lot easier. Okay, how would we tell if lines obviously that are parallel or perpendicular? Well, okay, but what if the right angle was missing? How would you know? You know, how would you prove that lines are perpendicular? What's the only way to do it? Reciprocal. You gotta show that the slopes are reciprocals. Yeah. Okay, we can probably dispense with this. What happens if the slope, well, let's look at these 2. So we get one slope is 1/2, the other one's 1/2. Obviously, those are parallel. Oh, never mind. We'll skip that part. I don't need to. You guys are fine. Okay, next issue. So now we kind of did a quick review of the forms of lines, slope. Let's look at how we can graph linear equations really quickly. Okay. How do we graph functions? Like we'll start off with slope-intercept form. Okay, slope-intercept form. We all know what that is. What is it? Y equals mx plus b. Good. Okay, m is the slope, obviously. What's b? Y-intercept, so hence slope-intercept. Okay, when you're graphing lines, here's how you can always summarize this. This is going to seem like there's a lot of steps here, but there aren't. Well, you tell me. How do you sketch a graph of a line? I'm going to distinguish between sketch and graph. If we're graphing something, what are we probably using? No, probably not. Even graph paper is not going to be perfect. An actual graph, which you might find on a calculator or on Desmos or something, right? So we're using technology to make a graph. In the modern, in real life, mathematicians would never graph stuff on graph paper. This would never happen. It's too inaccurate. But we'll do sketches of graphs a lot. Like in calculus, we have a whole section where we spend a month and a half, we spend about a month just practicing getting accurate sketches of graphs. And we don't really care if they look perfect, but we do want to know if the key points are in the right places. We want to know where, eventually we'll get to this with you guys. We'll talk about where we want to look for inflection points, or relative extrema, or things like that. And we've got to know the locations of those points because they're very meaningful in the real world. Like if we're talking about economics or we're talking about some physics issues, well, we need to know where those points are, but we don't need to spend time making the perfect graph. That's not really that big a deal. So we're talking about sketching graphs of linear equations. How do we do that? Just before we get specific, just completely generally, think about this strategically. How would you tell somebody much younger than you, who didn't know as much about math, if you wanted to help them sketch a line, how would you probably go about doing that? What would you tell them probably to get first before they create the line? 2 points, right? That's all we need. 2 points define a line, right? So all we have to do is get I'll call it an anchor point, and then a second point from that, and then just connect and extend, and we're done, right? So what if we're given an equation in slope-intercept form? Pretty easy. Where's going to be the first point that's going to be immediately obvious to it, that's just given to us? Yeah, the y-intercept, right? So we'll start at the y-intercept. How would we find the second point?
Balance up, you rise over run.
Rise over run. We'll make a slope triangle to get a second point, and then just connect and extend, right? So if the equation, either we can write it in slope-intercept form, which, by the way, just means writing it in simplified form if we solve for y. If we isolate y and simplify, it's in slope-intercept form, guaranteed. Then we start with the y-intercept, create a second point, draw the line. So where's the y-intercept? -2, voila. There it is. Slope triangles, we're going to rise by 3, run by 4. I would always do my slope triangles vertical first, so it's rise over run. I don't really like the way they did that. So we'd go up 3 and over 4. And then connect and extend, and you got it. Okay? So in real life, we use slope-intercept a lot. When we're using like a linear model to represent something. And I'm sure you've talked a lot about this. What does the y-intercept represent typically? It says it right here, I guess. Yeah, okay, but sure, mathematically on the xy plane. But what if we're talking about like a real world situation? When x is 0. So when the independent value is 0, what's usually going to be our independent variable 99% of the time? If you think about like these kinds of problems you've always done, the kinds of problems you'll do in physics or in science, other sciences, time. Yeah, usually we're looking at the evolution of some system in time, right? We want to watch how some system is growing with time, and we're going to model that mathematically. And then we'll talk about this a lot in calculus. This goes all the way up through differential equations in calculus. And so we call that the initial value, right? When t is equal to 0, that's x for us. And mathematically, but usually in a word problem, it's going to be t. And so that's the start value, or the initial value. What's m stand for? It's the slope mathematically. What's it mean in terms of like the real world context? What'd you always call it?
Steepness.
Steepness? No, I know, Mrs. Robinson. I have a camera this for. What's the slope always equal to? Starts with an R. Rate. Yes, a rate, isn't it?
Oh.
So if you're looking at something like this, if you're buying an $1,100 computer on layaway, you make a $250 deposit and then make weekly payments according to the equation right here. How much are you paying a week then? If this is the equation, there's B, right? Plus mx, but instead of x, it's t. So what's it going to be? How much are you paying every? $50. $50, right? That's your rate, isn't it? Okay. So your weekly payment's 50. If we were to graph this thing, let's just see the graph. Come on. Yeah, that was a lot of clicks for something you already told me, but I want to see the graph. I just want to make sure that you can start to make a connection between, man, making me work for this graph. Aren't you? Okay, there we go, finally. Does that make sense? Does that connect with that linear equation? If the linear equation is 850 minus 50t, or negative 50t plus 850, we can commute those, it doesn't matter, right? Does that make sense? That's our initial value. If this is the amount that we owe, it's just gradually, it's gonna linearly decrease until we hit the x-axis. Mathematically, is this line limited to the first quadrant?
No.
No, this line goes forever, right? But within our situation, it really doesn't make any sense to, for this to continue down. That would imply that, I don't know, you're continuing to pay like negative dollars. I mean, you wouldn't do that. You'd stop. It only makes sense in a certain area. We'll talk about that soon. It's called the domain, and we would limit the domain so it makes sense physically, right? But we'll get onto that soon. Okay, standard form. Here's the other form. You may not use this as much. Do you remember this form? Give me a 1 to 5 on this. 5 meaning, yeah, that's right, I remember this completely, perfectly. 1 meaning I never seen this in my life. Okay,
21 over 5.
somewhere in between. All right.
21 over 5.
21 over 5. That's what you're saying? Okay. All right. Take that. So standard form. Why do we do this in math, right? Why do we have all these different forms of equations? You'll see. Standard form is really important. In certain contexts, this is the way we want to do things. Other contexts, we want to have it in a different form, right? But you haven't used this probably as much. Standard form of a linear equation, instead of y equals mx plus b, is ax plus by equals c. Now, this doesn't really give you all the details here. I want to add a couple little notes for you. So a, b, and c, not only are they non-zero, they need to be integers. Okay, so we'd say a, b, and c are all elements of the set of integers. And there's one other additional point here. We don't like a to be negative. We'd like a to be positive. So a has to be greater than or equal to 1. Okay? What if a weren't, what if we got this equation and we had something like negative 3x plus 4y equals negative 7? What would I do to fix that, technically, to put it in standard form? Some people would accept that, but I don't like it. No, we don't have to do that. I mean, it'll work, but it's too many steps. There's one quick thing we could do. Multiply both sides by negative 1. What does that do to an equation?
Makes it
What's it do to all the signs of each term?
switches it.
Flips it, yeah. So that would make that positive, that negative, that positive, right? Okay, and then it'd be fine.
So B can be negative?
Yeah, B can be negative, C can be negative, but we like A to be positive. Okay, and we don't want any of those to be fractional. Those need to be integers. Okay, so if you've got something in standard form, there's a really super quick way to graph it. All you got to do is use what's called the cover-up method and find the intercepts. So let's look at an example. Like if we have, well, give us an example. Can I give us an example? Well, here's the method. Write the equation in standard form. Find the x-intercept by doing what? I mean, where is the x-intercept going to be? Where it crosses the x-axis, obviously. But what's always true with the x-intercept? Y is 0. Good. So we're going to find the x-intercept. We're going to find the y-intercept, which would be where x is 0, right? And then if we have those 2 points, it's really easy to just connect and extend. So let's do one really brief example. This is something, again, it seems like a pretty minor issue, but we'll come back to this later in the class in situations where it's a little more sophisticated. Like, what about this one? What's just by inspection here, just by looking, can you tell me what the x-intercept is going to be? And the way you can do this, if y is 0, cover that term up, right? That term goes away. If I'm going to let y equal 0, then I already know I'm creating a point with coordinates y is 0. What's x? 6. If we're going to let x equal 0, I can cover that term up, and y is 4. Okay, and then there are my points. Connect and extend, right? There it is. Okay. Questions? So another thing about standard form that's useful, we can't write a vertical line in slope-intercept form, right? Because the slope's undefined. So there's nothing to plug in for M. We can write both horizontal and vertical lines, though, in standard form. What's the equation of well, I guess there's a horizontal line, which makes sense. That works. That really is, you could think about that as either being standard form or being slope-intercept form, right? That fits y equals mx plus b, but what's m?
0.
0 if it's horizontal, right? So the m0 times x just goes away, and you just get y equals the y-intercept, right? Okay. So you can almost think about this, there's more to it, but it's kind of a mnemonic device. You can remember this always by just thinking about the weird lines, the horizontal and vertical lines you name by their intercepts, right? Horizontal lines don't have x-intercepts, right? They only have y-intercepts. So you name them by y equals whatever the intercept is. How are you going to name a vertical line? X equals its intercept, okay? Okay, so that's that. Last issue. I'm going to kind of accelerate this for you folks a little bit. I want to do the opposite of this now. So we talked about how we can graph lines. Now we want to reverse this, and let's see if you can remember or tell me, either remember or come up with a method. How are we going to write equations based on graphs, or at least based on information about graphs? You may not even need the graph. You could get the information from a graph a lot of times. You don't always need to. Let me give you an example. Okay, how about...
You said technically.
I did.
Yeah. One more time.
Oh.
It's not going to work at all. Okay. Thank you. It's important to keep an accurate count. Okay, what about this? Okay, I want you to tell me how you were told to do this. You guys obviously did this, but did you use point slope form of a line? Did you ever learn point slope form of a line?
Yes.
Okay, you did. We'll remind ourselves what that means, and then just as quickly we can abandon it, because you never really need to use it. Okay, does anybody remember what point slope is? Fill in the blanks. You don't remember. That's fine. What's that? Don't remember? Okay.
I'm gonna say it's about 3.
Okay, that's it. Okay, where's that come from? Because you're not gonna, well, you might remember that, but you can always really simply derive that. If we just start off with the definition of slope, definition of slope is y2 minus y1 over x2 minus x1, right? But if only one of the points is specified, then we would erase one of these sets of subscripts, right? Because we only have one point where we have known coordinates, like in this example, right? Not two. Then what if I wanted to solve this for y? What would the steps be in order to solve for y here?
Y minus 9.
Okay, but just in general, I don't want to plug anything specific in now. I want to try to start with this equation, and we want to isolate the variable y. Okay, I got to multiply both sides by x minus x sub 1, right? Okay, so step 1 would look like this. And if I multiply this side by the denominator, they'll cancel. Everybody agree? Okay. So on this side, I just get y minus y1. What's step 2? Well, nothing, I guess. I just flip it around, don't I? I mean, we can do that. It doesn't even count as a step. We can obviously switch contents of each side of the equation. We can interchange those. That's no big deal. So it's just really one step from the definition of slope to get there. Okay. What's this good for? Well, this is useful if we're able to plug in a point and a slope, right? You probably didn't learn that way, though. We don't really need to do it that way. There's another way, and this is the way I favor. You can take your pick, though. Either way is fine. I would say in this case that you start with slope-intercept, and what do? Yeah, you know M, don't you? Right? So if we're gonna, our goal here is to fill in the values of the parameters N and B. And I want you to think about this in terms of, what does this really mean? In calculus, in a couple of years, we'll talk about this as defining a family of curves. Okay, how many different lines can be described by that equation? What's all of them? How many is that? Infinite. So we're talking about all the lines on a plane. So let's say we're going to limit ourselves to the whiteboard up here, but pretend the whiteboard goes forever, right? It's infinite. We're just looking at a small piece of it, but it's infinite in extent. All of the infinite lines that you could draw on the whiteboard are defined by this simple equation. All you're doing here, there are two parameters, and it's not coincidental that a line is two-dimensional. We got two parameters here. You're essentially just dialing in values for M and B to get any conceivable line, right? An individual line is unique though, right? There's only going to be one line that's going to have a given value of M and B and none other, right? We call that one trajectory in calculus. We call that one trajectory of that family, that infinite family. So our goal is we just need to find the values of those parameters and we name the line. One of them is given to us directly, right here. But we got to find this guy, right? So step 1 would be we could just plug in the value of the slope. So that gives us y equals 8/3 x plus b. How could we find the value of b? And this is I really love this method because it brings a lot of things together that maybe you haven't been totally clear on. Yes, ma'am. Okay, we could plug in x and y. How come? If I draw this line, this is one point on the line, isn't it? Okay, so our line might look something like, this probably isn't accurate, but just bear with me here. So let's just say it looks like this. And here's a point way down here at -9, -20. There's a point that's on the line. Okay. What does it mean that this is a point that's on the line, but this point out here at 10:3 is not on the line? What's the difference? It won't work where? In the equation. It doesn't satisfy the equation. Remember, we said yesterday and before that if we talk about the solution to an equation, we're looking for the values of the variables that satisfy the equation, right? There are an infinite number of points strung together on this line, agreed? Every one of those points has an ordered pair that's a solution, right? They're going to satisfy the equation. So you could say then, one way of thinking about a line, hold on to your heads here, you don't want to explode. One way to think about a line is it's the infinite locus, or infinite, that's a fancy math word for set. It's an infinite set of solutions to the equation, right? Anything that doesn't fall on the line is guaranteed to be a non-solution. It can't satisfy the equation, right? That makes sense? So you can actually think about the line as being like if you have a wire strung tightly and you just put little beads on the wire, each of the little beads corresponds to a point. Where does that analogy fall apart though?
You can't fit
You can't fit an infinite number of beads on a wire. I mean, anytime that you, even if you focus in very, very closely on the wire, and you think you got two that are next to each other, how many beads actually should be able to fit between those two? Infinite, right? So, but you get the idea, right? So our goal is we just want to find, we want to find the values of M and B that are going to give us a solution. Well, we have one solution. We have this is one solution to our equation for sure. Those are the coordinates of a point that's on the line. So they have to satisfy the equation. They have to make the equation true, which means I should be able to substitute those in for X and Y, and they're guaranteed to work, right? So I can put the X value right there and the Y value right there, and they have to work. They're guaranteed to work. That gives us, if we do that, negative 20 equals 8/3 times negative 9 plus B. How many unknowns are there in that equation? One. If there's one known in an equation, we can solve it. We can isolate it, right? It might take a little bit of work, but we can do it. So what do we get? If we multiply straight across here, what's that give us? Yeah, we cancel, right? Negative 9 over 3 reduces to negative 3 over 1. So we get negative 20 equals 8 times negative 3. That's negative 24 plus B. Last step. Add 24, so B equals, we got it, right? So there's our equation. Now we can plug in B, and the one equation that's going to fit that information is going to be Y equals 8/3 X plus 4. Okay? Makes sense. So to summarize, we don't really have to use that point slope. We can just plug in the X and Y values from our point and solve for the missing parameter, the one that we're not given. Okay? So I'm going to give you a little harder one. How about this? Okay, what's our strategy going to be here? Math? I agree. Okay, yeah, this time look at the information we're given. Now, you're going to kind of get a sense, get some intuition about this, but when we're trying to find the equation of a line that's a two-dimensional object, right? Or one-dimensional object, but it travels through a two-dimensional space. So we're going to need to have two pieces of information, right? 2 points to find a line. Last time we got a point and a slope. This time we're given 2 pieces of information that ought to be sufficient. But how are we going to use it? I heard it over here. Okay, good. We could really use the same strategy with one extra step, right? The only extra step would just be, now we've got to calculate the slope first, and then use one of those 2 points, whichever one seems most convenient. Sometimes neither one is more convenient. Sometimes it is. So that's no big deal, right? We can do that. Okay, I'm going to skip that one because I want to do, how much time we got? 2 minutes. Okay, good. We want to do one more in here. Okay, here's a doozy. This is a granddaddy of all linear equation questions right here. So what in the world are we going to do? Oh, man. Okay, we don't have time to do this, but I want to take a second and read through this. I want to see if we can come up with a strategy. Write an equation in slope-intercept form for the line that passes through this point, perpendicular to the line that passes through those 2 points.
Oh, so you do that one, and then you do the physical with the other one.
Okay, go, Kendra, say it out loud.
Oh, okay. So you, okay, I don't know if it'll make sense, but you do the second 2 points, like the perpendicular one, and you find the slope of that, and then you do the negative reciprocal. So find
Okay,
the slope of
everybody see
the other
that? Good, so you got it. So we find the slope, take the opposite reciprocal, and there's our slope. There's a point. Now it's like the problem we just did, right? Okay. All right.
David's wanted to do that.